Oh, looks like I had the wrong banner going up then. Do apologise. Welcome back to the third NACAA stream for the day. And if that's the only thing to go wrong today, I'll be very happy. We hope you're enjoying today's streams. Remember, if you have any questions, please pop them in the chat. And if you're enjoying today's stream on Facebook, you can donate stars. On YouTube, you can donate stickers. And if you're watching us for the first time, please, and you're not following us, please follow us on Facebook. Follow the NACAA Facebook page as well. Like the NACAA YouTube channel and like the ASC YouTube channel. Our next presentation is by Janke. I probably said that wrong now. And it will be on the topic of smart telescopes. Are they a fad or functional? Since 2017, telescopes have emerged that combine optics, imaging, and computerisation. Although considered expensive, they promote portability, ease of use, and extraordinary performance, revealing dark sky objects from suburban locations. Detractors maintain you can assemble your own for less cost, but at what requirement in technical know-how and setup? Des has been an amateur astronomer since his early childhood, building a telescope in high school. He has been a continuous AAQ member for 21 years, in which time he's had many stints on the AAQ Council, and since retiring as an IT professional, he supports the USQ Centre for Astrophysics in public outreach and utilises the USQ's unique Unistellar eVscope to contribute to citizen science observations for SETI. Des, welcome to the stream, and we look forward to your presentation.
Thank you, Mark. And yes, no drama. Thank you, Mark. No drama. Your pronunciation was just fine, as we talked about before the stream started. So first of all, I'd like to acknowledge the traditional custodians of the land and waterways on which I give this talk, the Guyabal and Jarawar people of Toowoomba, and pay respect to elders past, present and future. So since 2021, I've had the good fortune to use what I'd call a smart telescope, and I'll share with you my experiences of one particular model and my thoughts on where I think this trend is going. Are they the future of telescopes, or just a gimmick that will have a niche following or eventually disappear? So first of all, what would I call a smart telescope? It's an optical tube with an image sensor that usually replaces the eyepiece or the secondary mirror, and integrated software controlled from a phone or tablet. So to set the context, I looked at image enhancement that's available for typical telescopes. And the first thing I came across was a thing called night vision, which is usually an eyepiece that attaches onto the either afocally or over the top of the existing eyepiece. And here you see an example of one particular one from Teleview. And its purpose is, oops, I got excited then. Purpose is to amplify the light coming to it, and usually shows the result on a phosphor screen. And this particular model, though, although the illustrations I've given there are from this eyepiece, it's not a cheap piece of equipment. The last time I looked, it was $4,000 US for this add-on device. So the next type of enhancement is electronically assisted astronomy, and that's watching an image from a telescope using a camera that's attached to the telescope, and that live streams that image then to like a monitor or a computer. So usually the image is stacked to give a brighter or clearer view over what you might see normally through the telescope using an unaided eye. So I found the key aims of this type of device setup is usually to reduce light pollution by reducing the noise of the succeeding images. You can use smaller and less expensive telescopes than you might otherwise have to get an equivalent quality image. And it has advantages such as it can be good for people with visual impairments who can't look through a normal eyepiece. And you can also have an audience that can view what the telescope is seeing. However, illustrated by my image there, I think it can have a complicated setup. It can be quite expensive to get all the pieces individually and make them all work. And it can often be difficult to make it portable. So how can I, have a variation on that? Well, this is the particular telescope that I've had use of for some time. It's a Unistellar eVscope. It's a reflector. It weighs about 7 kilograms. It's essentially a 4.5-inch f4 reflector. It has a Sony sensor that strangely only has a 1.2 megapixel resolution. But despite that, as you will see, it performs quite well, in my opinion. To keep things simple, they've just got an altazimuth mount on it, and it uses a wireless network to connect to an app that I particularly have on my smartphone. And it has an interesting history. Around about, I think it was 2017, the creators in France developed a prototype, and they showed it at an exhibition in Europe. And after that, based upon the interest they've generated, they created a Kickstarter project. And I don't know how familiar you are with Kickstarter projects, but there's some notorious failures there. But this one was fortunately quite successful. And when it concluded, it had over 2,100 backers, as you can see there, and raised 2.2 million US. And subsequently, the same people re-established a campaign in Indiegogo, which raised another 3 million. So quite a successful thing. And eventually they completed a unit for shipping and manufacture. And the particular model I received was ordered, I think, in 2020 and received by the university in late 2020. And of course, at the time, they made a lot of extravagant claims. So how does it work? So the images you see here are screenshots of the app on which I have on my phone. And a bit like a digital SLR camera, it has a live view mode where you can see what the telescope sees. This particular model also has an eyepiece on the side, which I would hesitate to call, and you might be interested to know, hardly ever use. Hence why the manufacturer now offers a model that does not have a on-device viewing option. The live view allows you to slew around and also take what's called an enhanced view, which essentially integrates the frames from the image and for however long you want, and presents you with the finished product, which you can then save to your smartphone. Now, the advantage of the smartness of it is that you can have up to 10 people also connected in as viewers, and they can also save that same image onto their device and take it away with them, as well as see what the integrated image is like. Now, as part of the operation of it, from time to time, I have to check the focus. And one of the useful add-ons that Unistellar provide is a Bartonov mask that some of you may be familiar with. It fits across the front and creates that cross shape that you'll see in the image in the center bottom. It makes it relatively easy to focus the object. So what sort of results does it produce? Well, here's some genuine images taken with the telescope. So you should see some familiar sites there. One is the Omega Nebula, Omega Centauri Nebula. And interestingly, the one on the right was taken at one of our society's viewing nights in the centre of Brisbane on an oval at the University of Queensland on a typically light polluted night. So you may be amazed as I am in the quality that it can produce. And that's, as you can see by the legend around the outside, if it's possible on that slide, about 1.25 minutes of integration. So here's some more examples. These were taken, the one on the left was taken at that same field night of the Jewel Box cluster, and the one on the right was taken at home. And as far as I can tell, there's no upper limit to the amount of time that can be spent on integration. That one was 8 minutes. And I found that once I get to about 6 to 8 minutes, continuing integration really doesn't help unless I'm looking for a particularly faint star or such. And here's some more examples. These are both 3 minutes, again taken from my home in Toowoomba. And there's a little bit of a story attached to these. So in October last year, the Society was asked if we'd go to central Queensland to present both first of all solar viewing and then at night night viewing for the school, and ended up being the community, and took the Unistellar eVscope with us. And the image on the right is the larger one, is a cropped image of the Ring Nebula, and you'll see a more realistic view, but that was taken on that night with that, which again, the children and their parents could view and see on their own phones and tablets and take a copy away. It was things like that first of all, the teachers at the school and members of the public posted then the next day on Facebook, and generated quite a bit of positive comments and interest, and hence one of the key sort of positives of this. And then, as is the want on the night, we asked people if there's anything else they wanted to see, and someone, of course, said, "Is there a galaxy we can look at?" October, galaxy, not a real good time, particularly about 8 o'clock at night. We were able to find the Sculptor galaxy, and as you can see, a minute exposure on the left is quite passable. Unfortunately, as well as it does on deep sky objects, I'm finding it's not as effective, this particular model, on the planets. These two are screenshots that I've taken, not enhanced stacked images. As you can tell from the titles on those particular images, the one on the left of Saturn is zoomed in about 8 times, and that's as good as it got. The one on the right I thought was pretty good, one of Venus, which I took at that particular central Queensland school night. And I've attempted to look at the moon with it, and it just is a hopeless washed out mess. It does come up with an okay image, but certainly not as effective as what would one find on a typical telescope. And so I guess I would not use it normally for this type of purpose. So one of the key advantages I find with the Unistellar organisation is that beyond just being basically a fancy camera attached to a telescope with related software, they also have a citizen science program wrapped around it, and it's driven by the organisation, and they work with SETI to analyse the data that amateurs collect. And the sort of areas that they operate in are near-Earth asteroids, asteroidal occultations, brighter ones, of course, and interestingly, they're quite heavily into exoplanet transits, and of late they've been tackling multi-continent ones, which are long transits, which require someone in one country to start and others to join in, overlapping the two observations so they can collect data across the whole length of the transit. Over on the right here, if you watch the title, you might see someone familiar pop up in it. This is a real video on YouTube that was taken of observations done of the near-Earth asteroid 2000 PQ9 last year. And data from that was sent to the Minor Planet Centre to help refine the observations. So again, very easy to do. So how does this telescope work? Basically, I cart the tripod out, which is quite sturdy. I mount the telescope on it after leveling the tripod, turn it on, point it down a little bit to a clear patch of sky, press a button on the live view screen, which effectively does plate solving. So it works out where it is. I presume it gets GPS and time data from my smartphone, and combined with what it sees, it works out where it's looking And within about a minute to a minute and a half, provided I've got some nice, reasonably bright stars in the field, it will work out where it is and it's ready to go. So at worst, in 5 minutes, I can be up and running. And trust me, it's really reinvigorated my interest in visual observing and getting outside with this, particularly in a field situation. However, with science mode, there's a little bit more to do. The app includes a reasonable database of objects, especially transient ones. So in this particular instance, the near-Earth asteroid would have been in the database. I would have typed in its coordinates, pressed go to, and then I would have come to this screen in science mode. You'll see there's a little academic hat down the bottom and highlighted in orange. And I'll put in parameters for the exposure time, the gain, the duration, which you'll see here is 10 minutes for this asteroid. Hit the launch button and away I go. And it will presumably image the asteroid about every 4 seconds. And the data from that is transmitted then after the run to the Unistellar people and lodged on the SETI server. Now, the particular asteroid I've illustrated here, I did observe, and this is part of the thing that makes it interesting as well, is there was something unusual about this asteroid. It was actually a trinary system. It had 2 moons. So there was particular interest in following this. So people all over the world observed this, Europe, US, I think there was some observations in New Zealand, and I think there was at least 2 people in Australia that also observed this. So I would have done 3 runs, 3 10-minute runs, taking a dark frame after each one and then re-go-toing the object to make sure it's nicely centered in the field, which I found is usually pretty reliable. And results from activities are generally very successful. There is actually someone's results from using one of these telescopes that's been in a genuine academic paper. And here's observations from people in Europe that produced a light curve on the left for a hot Jupiter around HD 189733. And there's a lot of that going on at the moment, very active observations of particular transits. And of course, depending on where you are in the world as to whether you'll even see it, they're particularly keen on TESS objects of interest. TESS is a particular satellite that NASA used for looking for candidate exoplanets. And these are followed up by a number of people. You may remember Chris Stocksdale's talk from last weekend's session. And as well, people in Unistellar network also do this. And on the right's another illustration of near-Earth asteroid observations. The top one is a GIF I made from 2 enhanced vision frames, and you're able to see the asteroid there moving against the star background. And down the bottom is an animation that Unistellar sent me of my observation. And as you'll see, they fixate on the particular object rather than keep the star field still. Unfortunately, it doesn't always go as planned, so I thought I'd give you some real warts and all information on what can happen with these things. Whoops. I'll just go back to that. So for this particular star, HAT P35, which is a well-known and confirmed exoplanet, I thought I would do some observations. It was in a reasonable position in the sky. The the transit ran from about 11:30 at night till 3:30 in the morning, and it was made up of a series of 40-minute observations. And unfortunately, each observation has to be started manually. A lot of the people in the network forum have been asking for some way to automate that. And I'll talk a little bit more about the implications of the manufacturer's approach to this later. But unfortunately, I made a bit of a bloop, even though I independently checked the transit time for it and thought, oh yes, the prediction from the Unistellar site was matching the transit time. I forgot that I needed to have a lead-in time and an exit time. So effectively, my observations were pretty useless. And as well, due to some collimation issues, which were identified by Unistellar by looking at the enlarged images you can see on the right, the data was so noisy, it was basically useless. So my 4 hours of observations were thrown in the bin. And I learned a valuable lesson. Since then, I've recollimated the telescope and refocused it, and I'm hopeful that it's better, but I haven't had another opportunity with cloud and presentation to do another one. But it doesn't always work. So there are some others out in the wild.
We seem to have just lost Des there for a moment. He's got a bit of an internet connection issue. So bear with us as we try to get him hooked back up. Here he comes. You're back. There we go.
Right. Sorry about that. Looks like our attempts to mitigate that didn't help that much.
Back into it. I'll leave it there.
Thank you. So I'll just revisit that I'm talking about another option for smart telescopes from the Vaillant company, which is also based in France. And the mid-range model is this one, the Stellina. And they are refractors. And this particular one is, as you can see from my slide, an 80mm doublet with an f5 f ratio. It has a much higher resolution chip, 6.4 megapixels, and some other useful features, but not having used them, I'm not sure how well they work. But or if it's as per the booklet, they'd be very useful, like autofocus and a dew heater would be very useful. They can connect more devices than the Unistellar one with 20. But a big difference here is, again, this is just a pretty easy to use and sophisticated camera. And as you can see below, it's a fairly expensive, sophisticated camera. And the manufacturer doesn't have any sort of citizen science program wrapped around it where you can extract and analyze the data that the telescope no doubt collects. And they are available in Australia. Bintel sell them, and when I checked on their price, it's $6,500. They have some more offerings too. They've got a slightly down market version, which is a smaller 50mm refractor, lighter 2 megapixel sensor, and some limited features, but then probably super portable and quite good to take around to a field night or whatever. And then at the other end of the scale, they've got a millionaire's toy, which is just obscene, I suppose, is the way I'd characterize it. Massive telescope, a 6-inch Apo refractor, so a triple element refractor. It has a massive 61 megapixel camera in it and numerous smart features. I remember looking over it and just couldn't believe how many things they could do. And I believe that it's intended that you could just set it up and leave it outdoors in the weather and it'll be just fine. Gigabit wireless network, USB ports presumably for removing the images rather than going it wirelessly. And for the small sum of $45,000 US, you can have one too. So the CEO is an interesting fellow. If you've got any time, you might like to search out Cyril Dupuy's presentations on YouTube. And in one of those, I found it interesting that he looked at why would you have a smart telescope. And one of the things he talked about was that some people are fixated with the equipment rather than the observing, and that they spend that much time preparing, operating, setting up and using their equipment, that's really the objective for what they're trying to achieve. Whereas what he saw was important was to build a telescope that was really easy to use and set up to encourage you to use it. And that's the best telescope, the one that you can actually use, which I thought was a very interesting point and a bit of a positive for these. So what do I think of smart telescopes? I think the positives are that they're meant to be and generally are portable. They're the secret to them is really the software. It's the Unistellar device, for example, has quite an extensive database of objects. It's easy to go to an object, and the features such as field derotation, which those of you who do astrophotography would be familiar with Alt-Azimuth mounts, is just done seamlessly. You don't even have to think about it. And that 8-minute image of the Trifid Nebula, not an issue with stars being out of alignment. It's just amazing. Very easy to set up, as you might gather from what I said before. A few minutes in any real location to set up, and it's just so easy to start seeing something and to capture images which other people can get as well as yourself. They're shared on my phone, and I can then use them almost immediately. Occasionally I do process them a bit, but I don't have to. Our society here in Queensland, we've also purchased one based upon the real life experience of using the particular one that I have. And our education outreach person, David O'Driscoll, finds it very useful for school nights and so on, particularly where his intention is to, for example, have an iPad with a large screen set up to operate it. And by putting that on a stand, as well as nearby people connecting to it with their own smart devices and viewing what it sees, he could also have an audience of people viewing what is presented on the iPad. So maximising the value of the sharing capabilities of it. And of course, as you've heard me wax on about the eVscope, the Unistellar telescopes, the citizen science program is something I think is a real strength for them, because once the novelty of the telescope's worn off as a simple and unsophisticated imaging device, it would probably end up in the cupboard, quite an expensive doorstop. But with the citizen science program, I can continue to use it all the time when the skies are clear to observe transits or asteroids or whatever, and make some contribution back to scientific knowledge. So I think that's a real asset and encouragement for this. On the negative side, as you've heard me already say, it's quite well suited to deep sky objects. It really does a fantastic job, particularly in a field night setting. However, as I've said, not knowing what the Vaonis is like, but the Unistellar one, I reckon they're fairly poor on the planets because of their short focal ratio and so on. So whether in future they come up with some mechanism to add optics in to make it better for planets or other objects that are facilitated by long focal lengths, I'm not sure. As well, in a practical sense, I found the Unistellar can have some odd behaviours. It really doesn't like looking anywhere above about 80 to 85 degrees. So near the zenith, it just doesn't track properly. The go-to can sometimes be a bit of a pain. And one of the related issues is you really have to have clear skies. I did successfully image Pluto late last year. I haven't put the individual images together to create an animation showing Pluto cross through the field, but I was able to collect some images. And one night I went out with banks of cloud drifting across, and by the time I tried to get it to plate solve and work out where it was, a cloud had come across, and then it'd lose the plot. And so I find that the inability to manually intervene and tell it where it is or whatever is a real pain. It's compared to a normal telescope where you can use a finder scope to point it at an object and just wait for the clouds to clear. It really doesn't cope with broken nights observing. So it can get lost to where it is, and then you basically just got to turn it off and start again. And as I hinted at earlier, one of the early things I saw was they were just pretty well focused on creating the telescopes. And like many commercial enterprises, there isn't a lot of interest in telling you a lot about how the telescope works under the hood. and they were a bit rough with the rigor of how they did things and revealing things. That has improved a bit in the last 6 months, but there has been a lot of calls, particularly from software developers using them, as to whether there could be application program interfaces or opportunities meant for people, even if they sign non-disclosure agreements, to add capability to the smartphone app and the intelligence in the telescope. And I'm finding that's where eventually the smarter users will outpace its capabilities to like download the data yourself and process it yourself, because some of the people using these are very clever. So what do I see as the future? I think they have a part to play. I don't think you all need to race out now and sell your normal telescopes and buy one of these. They're certainly very easy to use and a big winner at outreach events. I guess the analogy I like to think of is it's a bit like the transition from film to digital, perhaps not as dramatic, but there's possibly still devotees of the medium of film. And I guess I see smart telescopes compared to regular telescopes with attached cameras and guiding scopes and so on, computer controlled. There's a time when a compact camera is good enough, and the smart telescopes are just like that. Whereas when you want to do a long exposure or long focal length or something more specific, a normal telescope with the right equipment is like a digital SLR. There's a time you need that as well. But it certainly makes citizen science opportunities more accessible, and it's a great way to plug into research. So that's the end of my talk, and I'll just go back to here. And I see there's a couple of questions, Mark. I might be able to check and see that myself, if that's okay with you.
Yeah, I'll just pop them up on the screen. I'll just do what I normally do, read them out.
Yep.
Hi, Des. Dumb question, but can the smart scope be linked to a normal PC rather than a smartphone or a smart device?
Yes, provided it'll run the app. At the moment, the app only runs on iOS or Android. So I guess if you wanted to, you could run a Android or an iOS simulator and go from there. I don't know how much of the Vespa is. I don't know whether Bintel sell it, and I haven't bothered to check how much Vaonis is, but it's obviously less than the price of the Stellina, but I don't know how much.
Pete would like to know, is the collimation on par with a normal reflector for the eVscope?
It's weird. It's a pain in the neck. I have to use 2 Allen keys to move the mirror around, and it's very touchy. So as soon as you move the thing, the object disappears out of the field and I have to recenter it. I'm getting better at it, and I've manufactured my own tools to do it more easily and more reliably, but it's not too bad. So what I can do is check it by doing an enhanced vision image and zooming in on that. So it's not too bad. The focus is easy. It's just a large knob, and using the Barton knob mask, I found I can get that pretty well spot on. So I hope that answers your question.
So Jeff wants to know, how does it cope with issues like flat fielding as would normally be needed for exoplanet transit photometry? Good question.
Photometry. Yes, good question. Don't know. I think it's a fairly rough thing, so they'd go for fairly bright, or what's the term, large depth transits. I don't know how they compensate for the flat field. The field, maybe the software flattens the field fairly well, because I haven't detected any issue with that. But again, the exoplanet transit stuff's much more a data-driven thing. You can't see anything happening. It's more a set and forget. So I don't know, again, is an issue.
Murray wants to know, what is the Wi-Fi range, and could he have his smartphone or iPad indoors with the scope outside?
I think so. Because I don't want to risk losing my connection, I tend to leave my smartphone close to it outside. But I have wandered around the yard when I've been doing a less serious observation, like an enhanced view, and I can get about 20 meters away and retain a good connection. Let's see,
Ian,
where am I
thanks,
to?
Des. How did you acquire that eVscope? Last time I checked, Unistellar don't ship these to Australia.
Correct. Although I believe one vendor in Australia is now, particularly in Brisbane, is working at being an agent for them. The university bought it directly from Unistellar because of their nature as an educational institution and the intent to use it for research purposes, which is primarily 90% of what it is used for. The association, because of that, my relationship with Unistellar was able to take advantage of that as well. But you may have to talk. So if anyone's interested in following through and serious about that, then please make contact with me. You can reach me through President on the AAQ website.
Okay, so Tonin wants to know, all says, very informative, agree that the best telescope is the one that is used regularly. Will the software be regularly updated?
It seems to be. I've yet to find an object, yet to have come across an object that they want to observe that isn't in their database. But failing that, I can always, like a lot of go-to things, just put the RA and DEC in. So it does seem to be kept up to date to a degree. But as I said, it's got to the stage now where the power users are finding it a pain to use because they really like to get in under the hood and control the device or access the data directly. And I think there was a
last one from Doug. Fascinating talk. Do you think it is worth waiting until they develop the technology a bit more before a purchase?
Well, I guess it's a bit like buying a Tesla as a electric vehicle. You could wait another 20 years to get a cheaper and better featured device for a fraction of the price. I expect in time demand will drive the price down a bit. You could. So yes, I guess you'll know the time when the time's right. Personally, I doubt if I'd fork out the $4,000 to $6,000 that I'd probably have to buy one of these for myself. But maybe in 5 years the price may be more competitive.
Wonderful. Now I think that's all the questions we've got. Des, thank you for a very informative talk. To those watching at home, apologies for a little bit of technical difficulties there. Try not to have that happen again. I think some of that was actually at my end there, Des. I think I lost some NBN for a little bit just quickly in between all of that. Oh, we have one last question, actually, before we bring our next speaker in. John wants to know, what do you think of a video eyepiece for a standard telescope?
Yes, well, again, that's sort of what I touched on with the night vision stuff. It's not bad, but again, it's just about the cost of the whole setup and how difficult it is for the average person to get it all to work. Whatever works for you, it gives you more flexibility, more control. But again, for the average person, for want of a better term, that might be a little bit of a bridge too far, too technical. Whereas those of us that can handle that, not a problem. But the whole idea of this is you literally open the box, power it up and turn it on, and away you go.
It's the old KISS method.
Yes.
Yeah. Well, thank you very much, Des, for a wonderful talk. A lot of good questions and some great feedback as well, and very interesting product. I know we've got our AFTP section director is doing something similar with at our public outreach programs as well with his tablet. I think you're right, it's very much a way of the future for public outreach, that's for sure. It's a great way of showing people exactly what's happening visually without having to look for an eyepiece. You can, like you say, you can have 40, 50 people at the same time seeing the same thing, which is a big advantage when you're trying to get people into astronomy. Once again, thank you very much for your talk today, and we'll now bring in our next speaker, which is Peter. So Peter will be giving us a talk on basic meteorology for an observing astrophotography night. Peter will start by discussing how temperature and dew point relative humidity are related and work together. This will be explained using the examples of the kitchen kettle. I take my coffee black, no sugar, Peter. And bathroom shower mirror, and how they are related to cloud formation. Following this, Peter will run through the interpretation of bomb data, and Peter has been an amateur meteorologist storm chaser for many years, not to mention has a keen interest in astrophotography getting out there on the scope and doing long exposures. He also has taken many weather pictures, including lightning, as well as recording thunder in its full dynamics. His passions for weather and astronomy since childhood inspired him to put this presentation together, which he has delivered several times before to different sections of the Astronomical Society of Victoria. Peter, the floor is yours.
Thank you, Mark. And talking technology, fad or function, I have to thank you guys as producers, because if you didn't do what you do and keep the streams running, everyone out there would be looking at blank screens. So special thank you, and thank you to ASV and NACAA for hosting this event. So yeah, as has been already mentioned, my presentation is on basic weather for astronomers. Now, I'm condensing 50 years of experience into 45 minutes. So there's a lot I'm going to cover fairly briefly. So Mark's gone over the topics I'm going to cover, so I'll press on. Now, temperature and humidity. On a still night, humidity, or on any night, humidity is the amount of water the air can hold. Now, as the temperature drops, the amount of water vapor, which is tiny droplets of water that the air can hold, decreases. Think of the bathroom. When you put the shower on, the air fogs up. And in winter, it fogs up a lot quicker. Minimum temperatures for when you're out there on the scope are usually just before dawn. So that's when you've got the greater probability of your scope dewing up. For the same reason, clouds or fog are more likely to form later on at night, especially in winter. And of course, cloud cover slows the rate of temperature drop because it traps the air from our cities and towns closer to the ground. All right, the basics of weather in the bathroom and kitchen. This is one of my favourites. As I mentioned, clouds come from water vapour, which is tiny droplets suspended in the air. Now, if you take a kettle, as the water heats, the steam rises from it. Steam is water vapour, clouds or fog, which is clouds closer to the ground. It rises as it's more buoyant than the surrounding air. So if you're in a pool, if you push a foam ball underwater and let it go, it rises to the surface because it's more buoyant or less dense than the surrounding water. So it gets pushed up. With the shower, the room fills with steam. Because fog is just cloud or steam at ground level. If the steam touches a colder surface, as you all know, it condenses into water or water droplets. Think of the mirror in the bathroom. It fogs up, and as the droplets of water increase in size, like dew, the water runs down the mirror. Now, the colder the air, the less water vapor it can hold, which is what I previously mentioned. So dew will form on cold surfaces at night, more likely this time of the year than in summer. As a pointer, think of dew on the telescope outside on a cold night, like this time of the year, or even your breath when you're breathing. Now, rainfall forecast on the bomb. Now, a lot of people don't understand how this works, and it's fairly simple. In this example, there's 60% chance of any rain greater than 2 mil, 0.2 mil. That's what the chance of any rain, 60% means. Now, with regard to the 0 to 2 mil, there's 50% chance of 0 mil of rain, and there's 25% chance of, I'll start there again. There's 50% chance of 0 mil of rain, and there's 25% chance of 2 mil of rain. So it works on a sliding scale. So when you're looking at these rainfall forecasts, you need to keep these things in mind. Now, the weather map. Understanding a weather map, be your own Jane Bunn. You might think, oh yeah, right. But it's not as difficult as you think, or might think. Now, you've got high pressure systems on this slide, designated by the H, and you've got a low pressure, which is the L. Now, this chart was actually, I don't know if you remember, June last year. We had the cyclonic winds through Melbourne. It downed trees, crushed houses, all that sort of thing. Winds, roofs blew off, all that sort of thing. Now, I'll come to why that happened in a tick. Now, with high pressure systems, the air rotates anti-clockwise and descends. And the maximum air pressure is at sea level. So when you see on the chart, just going back, 1,028, 1,029, that's in hectopascals for you techies out there. That is the pressure at sea level, or if it's over land, at ground level. The temperature is greater lower down, so there's less clouds because the descending air is compressed at sea level. So it actually heats up. Think the tip of a bike pump. When you're pumping up a bike tyre, the tip of the pump is very hot if you dare to put your finger on it. With low pressure systems, or L designated on the synoptic charts, the clockwise circulating air ascends or rises. The pressure at sea level is the lowest. The buoyant air will rise, so it's less dense than the surrounding air. Think of what I said about the kettle. Now, clouds or rain or storms form due to water vapour condensing in turbulent rising air into cooler air. So with the low pressure systems, you've got air rising, it's relatively warm compared to the surroundings, it's got water vapour in it, it condenses, and you've got a lot of turbulent rising air. Think of the air, the way it circulates above a kettle when you're watching the steam. Isobars. This is one, I tend to poke fun at the TV presenters. On a weather map, the lines are lines linking areas of equal air pressure. Now, air will flow from high to low pressure. Again, think of a compressor or a bike pump, which is a smaller version. The closer the isobars are together, the stronger the winds due to the pressure gradient. So there's a lot of pressure in the air moving very quickly to lower pressure. Think of a compressor nozzle, or if you blow up a balloon and let the air come out, the air will gush out of the balloon because it's a stronger pressure inside the balloon. It wants to equalise with the surrounding air. Now, cold fronts on the weather map, or in real life, can force the isobars closer together. They effectively close the gradient or narrow the gradient between the highs and the lows. So you get stronger winds. Cold fronts, as I said, cold polar air undercutting warmer air, pushing up from Antarctica, I should say. Warmer air forced upwards cools, water vapour condenses, violent clouds forming turbulent air, hence thunderstorms. And this photo's an actual photo of a cold front pushing in. And as I said, tightens the isobars, so wind forms. Isobars being the lines on the weather map. So here's another graphic explaining the same thing. Highs are basically dry weather. We'll have cloud in the cooler months, like what we get now. And you have anti-clockwise wind circulating around them. Lows are bad weather, clockwise wind around them. And the closer the line spacing on the weather map, that's going to tell you the stronger the winds. Cold front, bad weather in winter, cool change in summer. As I said, is Antarctic air pushing up towards us. And it's on the weather map, the rose thorn graphic, if you like. Looks like rose thorns, as shown in this example. All right, satellite photos. Monitoring cloud conditions for observing. Now, I've deliberately got a satellite photo and the associated weather map or synoptic chart, so you can graphically see what's happening there. On the satellite photo, you've got a cold front coming across with an associated low, and the clearer air over the Tasman Sea where the high is on the synoptic chart. And the low pushing across pushes the isobars together or strengthens the pressure gradient. So you got strong northerly winds because the air circulates anti-clockwise around the high and clockwise around the low. Here's another example. This time, this is taken at night. And again, you can see the correlation between the satellite photo and the weather map. With the infrared or night satellite photos, the satellite takes heat signatures of the clouds, sea and land. So it's in shades of black or white. With the daylight photos, it's like you're up there looking down. And you, like with the camera, you take a photo. Now with the night satellite photos, the whitest parts are the coldest. The darkest parts are the warmest and everything in between. Now I shot this photo the night that the eclipse was on, May last year, the total lunar eclipse. And I was watching it very carefully. Now you'll notice the Port Phillip Bay there, for those Victorians, is dark compared to the surrounding land. So that's telling you that it's warmer than the surrounding land. The surrounding land is cooler. And with the clouds, or flecks of cloud in this case, the clouds are warmer than the colder than the surrounding air because they're higher up. And in this photo, the cloud was moving from the bottom left to the top right in this direction. And I live here, so I was watching this stuff evaporating very, very carefully. And it was a good night, actually. Totally clear skies. As I said, with infrared satellite photos, the cloud tops of storms will be very white, and they can be temperatures of -60, -80 degrees Celsius. The jet stream cirrus, which cirrus is those wispy clouds you'll see on a fine day when there's a front coming. On the infrared satellite photo, there'll be darker shades of white, and they'll be wispy in appearance, just like when you visually look at them in the sky. The mid-level clouds are around about 20 degrees Celsius and a brighter shade of grey. And the lower level clouds around 5 degrees Celsius, and they're darker shades of grey. Now, basic cloud types, what do they indicate? There's 3 general categories based on height. You've got strato, which is cloud to cloud on the ground, or up to around 12,000 feet, and they're generally in flat layers, and they indicate that a change or storm is either here or just passed through. The middle level clouds, or alto, between 12 and 20,000 feet, they can be layered or they can be heaped, cumulo, which is Latin for heaped, hence the word I used. And they can indicate a change within 12 to 24 hours. The high-level clouds, cirro, like what I mentioned, the mare's tails, the long streaks that you see on a summer's afternoon when there's a change coming in, although you can see them this time of the year as well. They're made of ice crystals, and they can be anywhere from 20,000 to 65,000 feet up. They can be layered, or as you'll see in the examples coming, they can look like cotton wool flecks in appearance. And they're generally above around 30,000 feet. And as I said, they totally consist of ice crystals and can indicate a change in 24 to 48 hours. All right, here's some examples. Here you've got hanging rock, and that's fog. That's stratus. You've also got stratus or fog in the top right-hand corner of the picture. And in the bottom right-hand picture, you've got a mix of stratus low down, you've got alto stratus mid-level, and you've got a bit of alto cumulus in here. I don't know if you can see my mouse, but across the middle of the picture, you can see they're slightly heaped. So they're designated as alto cumulus. Here are some more photos. You've got cumulus, obviously shot from the air. Pretty cool pic. Now you've got fractostratus, which basically means broken stratus. This shot was over Eildon Weir. Looks pretty cool. You've even got cloud reflections. Now mountain waves. Now they're a whole new topic. Pilots will steer well clear of them because, as you can see, the air is rising and sinking, and beneath you can have the air actually rotating horizontally in a circular motion. So obviously in an aircraft, you don't want to be anywhere near it. This left-hand shot is mountain waves from below, altostratus. And in the right-hand shot, you've got a mixture of, it looks like cumulonimbus almost, and you've got a bit of mammatus, which I'll come to in a minute. The stratocumulus, that's generally, you see that after a front's gone through. Down, I'm not sure about up north so much, but in Victoria, Tassie, South Australia and southern Western Australia, you see that, especially this time of the year, quite often. Top right-hand corner is what they call a mackerel sky. That's altocumulus, and you can see mountain waves, or they could be caused by terrain, yep, or it could be due to circulations in the atmosphere. But you can see it's got a wave formation. Bottom right-hand pic is a favourite of mine. I won't go into how it's formed in detail, but it's called a Kelvin-Helmholtz wave. So you've basically got colder air going horizontally across the top of warmer air. Colder going across the top of warmer air. So the warmer air rising, the colder air pushes down, and it forms these wave formations. Now, here's an example of cirrus. See the long streaks. This is shot at dawn. And the areas here, it's more cirrostratus. It's more a layer. It's not streaks as such. Classic cirrostratus here. You all would have seen the ring around the sun or the moon. Same thing. It's just a layer of ice crystals. You've got a couple of mare's tails. Good example. I'm not sure if they are in that shot above or below. Generally, they wouldn't be at the same level as the cirrostratus or the layered ice crystals. And the ring is caused by diffraction of the sunlight, in this case, by the ice crystals. So it gives that effect. Top right-hand picture, you've got cirrocumulus. Remember how I mentioned the cloud flecks? So where the cloud flecks are, you've got air rising, and in between you've got air sinking. So that's telling you the atmosphere up there is pretty turbulent. So it's generally indicative of a change or storms later on in the day. All right, how to make a good weather forecast for astronomy. As I said, I pushed through this pretty quickly, condensing 50 years of experience into 45 minutes, which is, pretty tough. But to make a good weather forecast, in this case for astronomy, for an observing night, of course, you look at the bomb forecasts. And not just on the night, you need to look at the forecasts in the preceding few days so you can get an idea of any trends. The synoptic charts or sat pics, and again, include 6-hour trends. Now, with the satellite photos, there's an option where you can actually play a loop so you can see which way the clouds are moving, how they're forming or evaporating, which is a pretty cool tool, and you can learn a lot from it. And you can get an idea of what the atmosphere is doing. Sky visuals. Look, get out there, point your eyes at the sky. Have a look locally, which way the clouds moving. And quite often you'll see them moving in different directions at different levels. Above all, gut feel. With experience, you'll get a gut feel as to what happens or what's going on, what might be happening down the track. But yeah, you've got to look out the window. Weather can't be observed from really being inside. You've got to be out there in it. All right, I'll very quickly brush through some of my photos that I've taken over the years. Left-hand shots, the martyrs as it's called, and you've actually got a microburst down here, the bottom centre. The way these are formed, you've got cold air being held aloft by surrounding warmer air. Like these bulbs are cold air, and they're being held aloft by surrounding warmer air. Now, if the surrounding warmer air cools, then obviously the colder air is going to sink, and yeah, you can get a microburst. And again, aircraft keep away from those. It can be like a jackhammer coming straight down, and it's been known to crash aircraft on takeoff or landing. Here you got a towering cumulus cloud, which eventually formed a thunderstorm, and you've got a layer cloud on top called a pileus cap. It basically indicates that the rising air has reached a barrier, and if it's strong enough, it will push through, which this did. Think back to the kettle when the steam rises and it reaches the bottom of the cupboards above. It momentarily stops there and then finds a way to continue out the front of the cupboards and keep going up. There's a UFO cloud. Now, it wasn't a UFO, but it damn well looks like it. I was amazed when I saw it. It was a summer afternoon. It's a cloud type called lenticularis, which I'll come to in a tick. Here, you've got what's called cumulus congestus with a really well-defined pileus cap. And you can see the top of it pushing through. Like I said, it's reached the level and the layer, the boundary layer, and strong enough to push through. Classic cumulonimbus. Everyone knows what cumulonimbus is. They've all heard of it. And note the well-defined anvil. Basically, the updraft of the storm reaches the top of the bottom layer of the atmosphere, and it can't go any higher generally, and it spreads out. All right, here we've got mammatus. As I got here, cows have udders, which are utterly disgusting. And that's what they look like, hence the name mammatus, which is Latin for, I think it is cow's udders, or it could be breast tissue, actually. But yeah, very distinctive and beautiful to see. All right, lenticularis. They generally indicate very strong horizontal winds, usually over hills or mountains. And you can get powerful rotors, which are horizontal rolling air, which are generally indicated by the tops of them. See the peak here. And as the temperature and dew point infringe, they cause reduced visibility. And yeah, the previous UFO cloud was a unique example. You've got a building cumulonimbus here. You've got low-level fog. This is shot from my place, which is stratus, and you can see the CBD in the background, 50 k's behind. anti-crepuscular rays. Now, when I took this shot, the evening sun was behind me. It's basically, if the humidity is high enough, the sunlight showing through or flowing through gaps in the cloud produces this striking effect. That's pretty cool. And yeah, there's a rainbow there as well. So very quickly, we've covered temperature and humidity, cloud and dew formation, interpreting BOM daily rainfall forecasts, understanding a weather map, understanding satellite photos or sat pics, as they're commonly called, basic cloud types with examples, and how to judge a good weather forecast for astronomy. So, yeah, just to finish, these synoptic charts and satellite photos or sat pics are courtesy of the BOM. All other pics are mine. So that concludes my talk on basic weather for astronomy.
Very interesting topic there, Peter. Some lovely photos too.
Thank you.
Now, I don't think there's no questions. We haven't had many questions today. I think the most we had was for
that's unusual. When I did this talk to the astrophotography section and of ASV and also the new astronomers, there were heaps of questions.
We have one here from Stuart. Stuart wants to know what sort of clouds signify good seeing conditions.
Basically, no cloud.
But say there's clouds about and you think it's going to clear, what sort of clouds would you expect to see if it's going to be clearing?
Okay, in Melbourne, you know the clouds that we've had during the day?
Those ones, yep.
They're basically middle-level clouds called anticyclonic loom. It's alto cumulus spread across the whole sky. That generally indicates for this time of the year stable weather. Now, hopefully, if the humidity drops and the air pressure is high enough, like a high coming in, that cloud will dissipate. So you'll have a clear night for observing.
There we go. Well, we need to know that with Melbourne because it's often clear and ends up cloudy. Lately, it's been clear during the day and got cloudy at night.
Yeah. It's frustrating.
It is. It has been. We haven't had very many clear skies. It looks like we don't have very many other questions. As I said, it's been a question-free day today.
I've got a few other photos I can share.
If you want, you can more than welcome to share a couple of others if you've
got no other questions. Yeah. Sure.
Yeah. We've got a little bit of time up our sleeves.
Yep. All right. Let me know when you're ready and I'll...
Yeah, all good. All good. I'm going to share that fresh screen and we'll...
All right. Being an astronomy event, I know they're not brilliant, but yeah, I'm happy to share some of my astrophotography. This is the Southern Pinwheel Galaxy, which I'm still working on, actually. Having a bit of issues, but yeah, that's another story. But yeah, as Des alluded to, it requires basically a computerized scope. It attaches to your computer or laptop, and you can get the scope to track the sky, track the object across the sky. Here's one of my favourite lightning shots. This was actually shot on Cup Day 2012. And yeah, believe it or not, there is a horse's head there. I did not even, when I took that photo, I only saw the horse's head when I checked it out on the computer that night. I was like, wow. You can really see the horse's head.
It's a very cool photo.
There's what's called cloud-to-cloud lightning. This went across the sky between clouds and pretty spectacular. The brightest areas are actually, remember, this is in 3D, so the brightest areas are where the lightning, that particular feeder, as it's called, is actually heading towards the camera. That's why it appears brighter. So you get an idea of the 3D aspect of it. That one was one summer's morning and that hit about 1.5 k's away. And so you can imagine the thunder that resulted. Yeah, that was a pretty cool bolt. I was not out there with the camera when I took the photo, obviously. I've got a good mate who's a pilot, and he calls me a crazy bee because he thinks I'm out there in it, and no, I'm under shelter. There's my background photo. That was shot Christmas Eve 2011. And the following day was when there was the tornadic supercells that dropped a twister near Bacchus Marsh. And there were some cool photos.
We have a question for you, Ian. Peter. We have a question from Ian. What about general haziness? And I saw this one and I'm like, yes, this has been a recent occurrence I've noticed. We've had quite a few days where daytime was clear and blue and nighttime has had a general haze.
Assuming there's no pollution of any kind.
We've had it out. We've had it up at LNDSS recently.
So again?
We had it at LNDSS recently where we've had clear days and you get it out at night and it's kind of a haze to it.
Yep. Assuming no moonlight and no pollution of any sort, light pollution included, it's an indicator of humidity. In fact, you'll see this time of the year in the afternoon, the sky might have a hazy look. That's due to humidity. In fact, you can actually see, if you look carefully around clouds this time of the year, you can actually see the water vapour before they actually form clouds. You can see it if you look.
Got another question for you from Clint.
Sure.
Do we get sprites in Australia?
We sure do. That's one thing I want to photograph so badly. Now, for those that are wondering what sprites are, when there's a lightning strike, and scientists don't understand what's behind it, but there are electromagnetic pulses and light pulses that shoot upwards into the atmosphere above the storm tops. And they were first actually observed by pilots in aircraft. And they can be photographed from the ground, but the storm has to be about 200-300 kilometres away from you, and obviously good seeing conditions. We definitely get them in Australia, yes, above any storm, anywhere. All right, here's some more, just as we close. This is the emu, which may have featured in some of the previous talks. And that's from Indigenous Astronomy. You've got the coal sack here. There's the Southern Cross, the neck of the emu, and then, there's the body of the emu. And that's as it was rising. That was a 30-second shot with a DSLR. Anyway, I think my time's about up. I'm happy to keep going, but I think time's up.
It is. So bring us back on screen and thank everybody.
Thanks again for you guys in the background there, because without your work we wouldn't be here.
We do. We've got a team of guys or team of people in the background. No one can see at the moment. We've got Stuart hiding in the background moderating and helping out, and Andrew Hayes as well helping out in the background. We've had a whole lot of guys from the AAC giving us a hand throughout these streams.
Special thanks to all of them, because it wouldn't happen if it wasn't for them.
It's been a lot of fun.
NACAA for organising it, and ASV.
We have one last stream to go, which will be kicking off at 3:30, and we'll be covering topics relating to saving the dark, the global Allen network, and introducing Big Skies collaborations inland astro tour routes. Don't forget, you've got until 4:30 to grab a raffle ticket for the raffle draw, which will be drawn at 5:30 this afternoon. asv.org.au. There's a ticket link on the site. $5 ticket goes to the ASV Remote Observatory project. As I've said in the last few streams, if you're not already following the ASV or NACAA on YouTube and Facebook, please do. Be greatly appreciated from both NACAA and the Astronomical Society of Victoria, and you'll get plenty of good content throughout the days and weeks and years ahead. We'll see you back here at 3:30 for the final stream of NACAA 2022.